All right, so let's take a look at the lesson we're doing today. So today's lesson, we're going to investigate two more integration techniques. One is using long division, yay, and the other one is completing the square. I know y'all are excited about that, that algebra. Okay, so here we go. So the first one, we have two examples where we're going to practice long division. So the first thing we have to remind ourselves is, how do we do long division? You may or may not remember from your previous classes, but the expression in the denominator becomes the divisor, right? That goes in outside of our little box. And the expression in the numerator goes under the, if you will, box, whatever you want to call it. So 3x cubed, let me just make this bigger, minus x squared minus 5x plus 1. If you recall from our work with long division, if we're missing, let's say we didn't have an x squared term, do y'all remember what would we put in place of the x squared term? Remember that? Like a 0x squared, right? Like a placeholder. Okay, I'm just reminding you, if we don't have the variables in descending order, 3, 2, 1 constant, then we need to insert what we don't have. Okay, well, that's what we would need to do. So just remind you, so we take the first one here and we ask how many times will it go into the first one? That's what we do. It's always first to first. So how many times will x go into 3x squared? Or in other words, what would I multiply x by to get 3x squared? Okay, I would multiply it by 3x cubed. I would multiply by 3x squared because 3 times 1 is 3. X squared times x is x cubed. And then if you recall, I have to multiply to both of them. So 3x squared times a negative 2 would be a negative 6x squared. I draw my line, and I always put a parentheses and a subtraction because, very easy to forget to distribute or think about we're subtracting and not adding. So I'm going to pause here for a second. That's my first go. How are we doing?
Wait, hang on. How did you get that in divided by?
So I have to ask myself, how many times, so I'm looking at this and this, and I have to ask myself, well, really what I think of is, what would I multiply x by to get 3x cubed? That's the question I ask myself. What would I multiply x by to get 3x cubed? In other words, what is 3x cubed divided by x? Well, that's 3x squared. So 3x squared times x is 3x cubed. Great. They should net out to 0 always. Right here, the variable that you pick should always make this term go away. If it doesn't go away, then you picked wrong. Okay, and then I distribute that out to the 2 as well. How are we doing? Are we okay? All right, so now we go on our next go round. I've got to subtract. So 3x cubed minus 3x cubed, that goes away. So negative x squared minus a minus 6 would be plus 6, right? Negative x squared plus 6 would give me a 5x squared, and then I bring down the next term. Now we go again. Now this time we're going to see how many times will x go into 5x squared. Okay, so let's see. Or in other words, what would I multiply x by to get 5x squared? Let's see, I would multiply it by 5x, right? 5x times x is 5x squared. 5x times a negative 2 is negative 10x. I stop and I subtract. Again, the first term should always go away if I picked appropriately. So 5x squared minus 5x squared is nothing. Negative 5x minus a minus 10x. So negative 5x plus 10x would give me 5x. And then I bring the next term down. And I go again. So again, I'm looking for what would I multiply x by to get a 5x, or what is 5x divided by x? It would be 5. So 5 times x is 5x. 5 times negative 2 is negative 10. Again, I'm subtracting. So 5x minus 5x goes. So 1 minus a minus 10. 1 minus a minus 10 is 11. Now this is our remainder. Okay, this is our remainder. And we usually always have a remainder. I'm not going to say it's going to be always, but it's normal to have a remainder. So what do we do? What are we going to do? What we're going to do is we're going to rewrite this integral where this part right here is the whole part. Think of this as the whole part. This is whole. And this part down here is the fractional part. This is the fractional part. And we're going to rewrite it so we have like a whole part and a fractional part. So we integrate. The whole part is the 3x squared plus 5x plus 5. Okay, that's the whole part. The fractional part, if you recall from previous math classes, I would write this fraction as, remember, it's 11 over the divisor. Remember that? 11 over x minus 2. Okay? Uh-huh.
So when you did the 5x squared,
Mm-hmm.
how come you didn't multiply it by the negative 2?
Because what I'm doing, the negative 2, what happens to the negative 2 is it comes into play with the numbers up here, with these up here. These are the ones that are going to multiply to the negative 2 every time. This multiplied to the negative 2 and it got me negative 6x squared. This multiplied to the negative 2 and it got me negative 10x. This multiplied to the negative 2 got me negative 10. That's where the negative 2 comes in.
Okay.
It's the multiplying back out business.
Oh, I see.
Okay? Uh-huh. Other questions? Okay. So as we're looking at this integral that we're going to have to do, I hope that you recognize that this part right here would be a u sub. Now, what I typically do is I typically leave it in the integral and I do it in the whole integral. But if that troubles you and you don't like that, you can split that into two integrals. It is fine. I'm going to leave it together and I'm going to put to work out to the side. Okay? Here u would be x minus 2, du would be dx. So really what I would be doing is I'd be integrating this. So I just write myself little notes out there. But you don't have to. I mean, you could just split the integral and do it completely separately if you want. So I'm going to pause here for a second. So this little piece needed to be u subbed, and I did it out to the side. How are we doing? Okay, so now I'm going to do the integration. So this is a reversal power rule, right? I add 1 to 2 and I get 3. And then I divide by 3. Plus, I add 1 to 1 and I get 2. And I divide by 2. Plus, I have just a constant. If I'm integrating a constant with respect to x, it just tacks an x onto it. This right here, hopefully we know 11. If I integrate 11 over u, what would I get? ln u, right? That's what I would get. I would get ln u. So I would get 11 ln u plus c. That's what I would get. And now I'm going to clean it up and put the u back in. So that gives me x cubed plus 5/2 x squared plus 5x plus 11 ln of, my u was x minus 2 plus c, and I'm done. This technique uses long division. Okay, I'm going to pause here for a second. How are we doing?
I'm a little confused about like the division of like the 3 divided by 3 and then 5 divided by 2.
Oh, that's so the rule for, if we're going to integrate x to the n, okay, dx, what we would do is our formula is we would do n plus 1, and then we would divide by n plus 1. That's our formula. So that's just the formula.
Oh, okay.
Yep, I'm just doing a formula.
I see. Thank
Okay,
you.
you're welcome. Other questions? We're going to do one more like this. So hopefully after the second one, it'll be even better. Are we okay? Okay, let's go to our second one. I want to pause. Actually, I want to pause here for a second. Look at the way this looks. I want you to look at this. That looks pretty complicated, right? I've got a fraction. It's a rational expression. I have an x cubed over x. It's improper. It's an improper rational expression. I am going to usually do long division on those. That is the technique. If you have, this is called an improper, if I could spell improper rational expression. That's what it is. So rationals, if you recall, is like a polynomial over a polynomial, right? That's a rational. So I've got a polynomial of a polynomial. Since the exponent, the leading exponent in the numerator is greater than or equal to the denominator, it's improper. Okay, it's improper. It would still be improper if this were an x to the first power. It has to be, to not be improper, this degree needs to be smaller than the denominator degree. Okay, really important. Otherwise, you're not going to know when to do this. You would do this technique when you have an improper rational expression. Okay, are we okay? So let's look at the next one. First of all, is it an improper rational expression? Yes, it is. This is to the fourth power. This is to the first power. That's improper. So I'm going to do this technique. I'm going to divide. I'm going to do long division. So let's practice long division again. All right, so recall, we put the denominator outside of the little box or house or whatever you want to call that thing. And then inside it's going to be 6x to the fourth minus 7x cubed plus x squared plus 2x. And I don't have a constant, so I'm going to put plus 0 there. Every time you don't have something you should put a placeholder of a 0 in there. Just a reminder from our previous work. Okay, are we okay? So again, I'm going to take, I'm dividing the first term. Even if there are like 4 terms out here, I'm still just going to divide the first term. 3x goes into 6x to the fourth. I'm first to first. In other words, I like to think of it as multiplying because that's easier. What would I multiply 3 by to get 6? I'd multiply by 2. And what would I multiply x by to get x to the fourth? X to the third. That's what I would do. Right? That's what I would do. Now I have to multiply back out to both of those terms. That's where the second one, or however many of them there are, comes into play as the multiplying part. So 2x cubed times 3x is what? 6x to the fourth. 2x cubed times negative 5 is what? Negative 10x cubed. So we stop and I put parentheses and I put a subtraction sign. All right, let's see, 6 to the x to the fourth minus 6x to the fourth, that's 0. So negative 7x cubed minus a minus 10x cubed, which would be negative 7x cubed plus 10x cubed, which would give me a 3x cubed. And I pull down my next term. And I'm going to pause. Okay? So again, I'm working with the first and the first. So 3x goes into 3x squared. Let's see. Yes, this one is cubed. All right, so we have 3x goes into 3x. So 3 goes into 3 one time, so don't have to worry about that. X goes into x cubed, x squared. Or in other words, what would I multiply 3 by to get 3? 1. What would I multiply x by to get x cubed? X squared. All right, so 1x squared. Now we multiply back out. X squared times 3x is 3x cubed. X squared times negative 5 is negative 5x squared. I stop and I put my parentheses and a subtraction sign. So let's subtract. 3x squared minus 3x squared is nothing. X squared minus a minus 5x squared. What is x squared minus a minus 5x squared? 6x squared. So I have 6x squared, and I bring my next term down. Okay. So again, we're just working with the first term. So 3x goes into 6x squared. In other words, what would I multiply 3 by to get a 6? It would be a 2, right? What would I multiply x by to get an x squared? It'd be an x. Okay, so let's multiply back out. 2x times 3x is 6x squared. 2x times a negative 5 is a negative 10x. I stop, I subtract. Okay, 6x squared minus 6x squared is nothing. 2x minus a minus 10x. 2x minus a minus 10 would be 2x plus 10x, right? Which would be 12x. And I pull down the last term. Okay. Again, working with the firsts. 3x, what would I multiply 3 times to get a 12? You have 4, right? What would I multiply x by to get an x? Well, 1. I don't need to worry about that, right? And so now let's multiply back out. 4 times 3x is 12x. 4 times negative 5 is negative 20. Okay, subtract. 12x minus 12x is nothing. 0 minus a minus 20 is a positive 20. Okay. So again, this is my remainder. And this is my whole part. That's the whole. That's going to go into the integral just like it looks. Okay, here we go. So we've got the integral of 2x cubed plus x squared plus 2x plus 4 plus, now how do we write our remainder? 20 over what? 3x minus 5. Okay. Are we all right? Okay, so the whole part is going to be easy to do the antiderivative of. That's easy. We have a little u sub right here, so I'm going to keep it in where it is, and I'm just going to circle. And I'm going to say u would be 3x minus 5. Du would be 3 dx, or 1/3 du equals dx. That would be my u sub part. If I were to rewrite it, we would do 1/3 integral of 20 over u du. That's what we would do, right? That's what we would do. 1/3 integral 20 over u du. All right, so let's start our integration. So I'm doing antiderivatives, right? So I'm adding 1 to 3, so that gives me 4, and I'm dividing by 4. Plus, I'm adding 1 to 2, so that gives me a 3, and I'm dividing by 3. Plus, I'm adding 1 to 1, so that gives me 2, and I'm dividing by 2. Plus, I have a constant. So a constant, integrating a constant with respect to x, you just insert an x by it. Then I've got my u sub, right? So it would be 20 over 3. That would be my constant. The antiderivative of 1 over u would be ln u plus c. Okay, now we're just in our cleanup phase. So I have 1/2 x to the 4th plus 1/3 x cubed plus x squared plus 4x plus 20 over 3 ln of 3x minus 5 plus c. Okay, so those are two examples on using the long division before we integrate. All right, how are we doing? Okay, we have one more technique we're going to look at today. Actually, the last one in this unit, the last integration technique that we're going to do. And that is on the next page. I have a couple of examples on that. We are going to use completing the square to rewrite the integrand. So vocab word, integrand, do you remember what that is? Integrand, that vocabulary word? That's all this stuff inside here, right? That's the integrand. Okay, So when we look at this, we couldn't do long division on it. That's not an improper fraction, rational fraction. So there must be another way, and this is the way. Now this is a weird thing, so I'm just gonna say we're completing the square. Some of us remember that with fondness, some of us remember that with terror. I don't know which camp you're in. If you remember that like, oh yeah, that's easier. Oh my gosh, what is that? I don't know where you are, but we're gonna work through that. So what do? I pull out the parts. This is just scratch work, okay? I'm not doing the integral work right now, it's just scratch work. So I pull out the part with the x's in it and I move the constant to the side. Please, please do not try to include the constant in your work of the completing the square part. Do not. Move it to the side. I don't care what it is, move it to the side. So let's remind ourselves how to complete the square. This is b, right? The location we call b. I half b, half of 6 is 3, and then I square it. 3 squared is 9. Now, what did I do to this bottom, the denominator? I added 9 to it, so I have to counter it by subtracting 9. Right? I'm just not allowed to go in like willy-nilly and just add stuff without accounting for it. So I want to pause there for a second. Are we okay and understand that if I add 9 and subtract 9, I really haven't done anything? Right? We're still at the same value. It's the same value. So now what I'm going to do is this is the part that is the perfect square, right? This is the part we did the perfect square to. And so now what I'm going to do is I'm going to rewrite it in like factored form. So let's see, that would be what? This would be x plus 3 squared plus 1. Okay, that's just the completing the square work. And so I'm just going to circle it right here.
How did you get?
Which one?
How did you get the 9s there again? Sorry, my thing was completely.
Oh, no worries. So the rule is, I'll put it up here. So the completing the square rule is you take half of b, and b is, the number in front of the x. This is b. You take half of b, then you square that number. So half of b, which is the number in front of x, then you square it. So half of 6 is 3, 3 squared is 9, and then I have to basically do the opposite. If I'm adding 9, I have to subtract 9. If I'm subtracting 9, I have to add 9. I have to net it out to 0. Okay? All right, so this part right here is the completing the square part. That's what that is. That's just completing the square work. So now I'm going to rewrite it into the integral. So I have 1 over x plus 3 squared plus 1. Okay. So what I want you to think about, and we're going to do u sub next. I want you to think about, does that look close to a derivative that you know? Close. Yes, that is arctangent. That is almost perfectly arctangent, isn't it? Okay, so what is the weird part? The x plus 3, right? That's the weird part. So we're going to say u is x plus 3. du would be dx. So I'm going to rewrite this as the integral of 1 over u squared plus 1 du. Okay, so we know what that is, right? That is arctangent. So my answer is arctangent, and you can, well, I don't like using the little -1, but you totally can. Arctangent of u plus c, and we know u is x plus 3, so our final answer is arctangent of x plus 3 plus c. Now you can write arctangent, or you can write tangent to the -1 of x plus 3 plus c. It really doesn't matter to me which one you do. I just typically do arctangent because I think the -1 and the exponent is just weird. Okay, so that's completing the square. How are we doing? We have one more example like that. Are we okay? Yes? Okay. So let's do one more example.
So we don't always have to take the inverse tan.
No, it's just going to depend on what kind of formatting thing we have. What does it look like?
Okay.
Okay? All right, here we go. So let's do our completing the square part. This one is a little bit more challenging. It's got a negative, so let's remind ourselves. So I take the x parts and I pull them out like this, right? But if you remember from completing the square, I need to move the 15 over here, right? We're just going to keep that over there. If you remember from completing the square, doesn't this have to be a +1? Y'all remember that? It has to be +1 right here. This coefficient needs to be +1. It's not. So what do I have to do? I have to factor it out. I have to factor the negative out, which changes the middle sign. And I'm just going to pause right here and make sure we're okay. Because I am not allowed to complete the square with anything except a 1 leading coefficient.
Why would you change the sign of the 15?
So the 15, I don't want to hurt its little feelings, but it doesn't get to play. It just moves out to the side. We don't mess with it. We just add or subtract whatever we need to from it. But we do not make it part of the completing the square. It's just pulled away. Okay, no matter what the number is like over here, we pulled away the 10, right? We just got it out of the way. We're just going to deal with it later. That's what we do always. We always do that with the constant when we're completing the square. Always just get it out of the way. Okay, any other questions? Okay, so now we're going to complete the square. So half of 8 is 4, and 4 squared is 16. Now I added 16 here, but did I really add 16?
No.
I did not, did I? What did I really do? I really subtracted 16. So to counter it, I have to add 16 here. Okay, this is the completing the square part. I'm going to pause. Are we okay? Okay, so let's factor this. So this would be what, x minus 4 squared plus 1. This is the completing the square part. Okay, this is just the work for completing the square. Which, to be honest, is the hardest part of these kinds of problems, is the completing the square part. Because the integration is pretty easy, because it's just a formula. Okay, so let's put it back in. All right, so I've got 3 integral of 3 over the square root of negative x minus 4 squared plus 1. Now, that looks very familiar, but it's kind of a little bit in a wrong order, isn't it? I'm just going to rearrange the way it looks. So 3, and then I have the square root of 1 minus x minus 4 squared. Okay. Do we recognize, so this should look very similar to a derivative that you should know. It's the arcsine derivative. It is. It's the arcsine derivative. And what would we make u? X minus 4. Very good. X minus 4. Du would be dx. Okay, so we've got the integral of 3 over square root of 1 minus u squared du. And we know that is arcsine. We just talked about that. So this would be 3 arcsine of u plus c. And I know what u is. We already told it. So it's 3 arcsine of x minus 4 plus c. All right, how we doing? All right, so we have one more thing to look at, and this is an overview. We're going to look at the integration techniques that we've learned, which are over here in this little table right here. And what we're going to do is we're going to look at each of these problems and we're just going to decide what we would use. That's all we're doing. We're not working the problems. We're just deciding what technique would we use. This is important, right? Because they're not going to be instructions above your problem that say, oh, use this. You're going to have to figure it out on your own. So we need to understand what we should use. So let's focus on number 5. Well, first of all, let's go through these. So we got the reversal power rule, right? What do we use this on? We use this when we have like, x squared plus 3x, something like that, right? That's what we use for that. Use substitution, right? We know when we use that, it's when it's close to a formula, but not quite. When it's close, but not quite. Trig is, well, when we have trig, sine, cosine, those kind of things. Inverse trig. Inverse trig is when we have these, like 1 over 1 plus x squared. If it looks like this, we would use inverse trig. Exponential and logarithms, well, it's like, 2 to the x or e to the x, whatever, e to the x. And we don't, in this course, we don't do single logarithms. We don't do the antiderivative of single logarithms because it takes a technique that we don't learn. So this would be like the logarithms would be just a u sub if this were a u sub. I know you're probably sad. You really want to learn that, but I'm so sorry. We just don't have time to learn integration by parts. Sorry. Long division. When do we do long division? When we have improper. When we have an improper, we have improper rational. That's when we do long division. When do we do completing the square? When we have some kind of quadratic, right? That's not in, like, we can't factor, it's like, so we complete the square with a quadratic and we hope for inverse trig. Algebraic substitution, we learned that last time. When do we do algebraic substitution? Extra x's. And you had one on the practice today. You see that at the very bottom, the exciting one? Yeah. This is with, we have extra x's. Okay, so here we go. Stay with me. What are we going to do on number 5? We're going to do trig. Would you like me to write the numbers here or the word? What do y'all think? The word? Okay, so we would do trig here. Okay, what about number 6? What will we do there? What do you think? Completing the square. Almost. It's not improper, or we would try long division. It's got a radical. That's a problem. This one will be completing the square. Okay, what will we do on number 7? Exponential techniques. And we have a formula for that. Okay? What would we do on number 8? Inverse trig. Okay, I'm going to scoot it up a little bit. What would we do on number 9? Almost, yes, a version of u sub. Which one? Algebraic substitution, because there's extra x's there, aren't there? This one is algebraic substitution. What would we do on number 10? Well, first we would distribute, right? We would distribute, and then what would we do after we distribute? Power rule, absolutely. Distribute, then power rule. Very good. All right.